Because atoms are so small, it's impossible to measure them conventionally. How can we add a mass to something where the typical way to measure that mass, like a scale or something, is actually made up of what we're trying to measure? It doesn't make sense, so we came up with this imaginary unit called the atomic mass unit. The definition of this is the mass of a single proton or a single neutron. This does not have a conventional unit and is in no way tied to grams, kilograms, or any regular mass measurements. It's kind of like how length is in meters, volumes in liters, grams and kilograms are for mass, and then atomic mass units is atomic mass units. A mole is not a mass or volume measurement. Instead, it is a countable measurement and is approximately 602 sextillion particles. The number of atoms or compounds in a mole is always constant. This number of things always stays the same. We have 602 sextillion hydrogen atoms in a mole if it is unbonded monoatomic pure hydrogen. If it was water, H2O, we would have 602 sextillion water molecules, which would mean we have double the number of hydrogen and 3 times the number of atoms overall, no longer 602 sextillion atoms individually. Why is the number of atoms in a mole so weird? Well, as previously mentioned, this number is known as Avogadro's number and is almost exactly the number of atoms in a 12-gram sample of carbon-12. Atoms are so small that we gave them the imaginary unit of atomic mass unit to describe their mass, but it doesn't have any bearing on conventional mass measurements such as grams or kilograms. I can't say, oh yeah, how many grams of atom do I have? That just doesn't make any sense. If we say that a mole of a substance is the number of particles we need to have the same number of grams as we have atomic mass units in a single one of these particles, yay, we've got grams! So this number is so specific because in order to convert from the atomic mass unit to grams per mole, we needed to have this exact number of particles. If we have any element or molecule which has a certain atomic mass unit and we have a mole of them, the number of grams that this substance sample will always be the same as its number of atomic mass units per particle. That is why the number is so specific, because atoms haven't conformed to our definition of grams. That's a concept that we've made up, but we can't control atoms. They've decided that they want to be one atomic mass unit, and we've decided that gram has nothing to do with the atomic mass unit unless you multiply it by 602 sextillion. Despite this, why are all the mass units not whole numbers? I thought we were only using protons and neutrons. Yes, however, isotopes. The issue with isotopes is that atoms with the same number of protons but different numbers of neutrons are chemically the same and have almost all the exact same properties. This means that in chemical bonds, such as ionic and covalent bonds to create molecules and compounds, the atoms don't care whether they're bonding with a carbon-12 or a carbon-13 or even a carbon-14. This means that we had to find a way to standardize it. Since there is not an even distribution of all the isotopes in the universe, we'll get an average of one element's isotopes, then we can calculate its average atomic mass. Hydrogen has a mass of 1.008. This is because most of the hydrogen in the universe only has one proton, so one atomic mass unit. However, there is a little bit of hydrogen with one proton and one neutron, meaning 2 atomic mass units, and there's a tiny bit of hydrogen with 1 proton and 2 neutrons, meaning 3 atomic mass units. If we calculate the average of all these isotopes, then it is slightly more than 1 atomic mass unit, and that is the relative atomic mass for hydrogen. How do we calculate this average? Simple. We get the mass of one isotope and we multiply it by its percentage distribution in the universe. If one isotope constituted 80% of all the atoms in the universe, we could do that isotope and multiply it by 0.8 or 80%. We can then sum it with the other isotopes and multiply it by their percentage distributions. Keep in mind the percentage distribution of every single isotope should add up to 100% or 1. After undergoing this process, we get the number that is listed on most periodic tables conventionally and is known as the relative atomic or relative molecular mass, which can describe either the mass in grams per mole or the average number of atomic mass units in a single atom or molecule. The atomic mass of pure carbon-12 is still exactly 12 grams per mole or 12 atomic mass units. However, there is a tiny bit of carbon-13 in the universe and there is a very little bit of carbon-14, although being radioactive. This means that the overall relative atomic mass of carbon is 12.01. This is because if we had a sample of carbon, we would expect most of the atoms that make it up to be carbon-12, and so if we had a mole of it, it would be almost 12 grams. However, we do expect that there would be a couple of carbon-13 and possibly carbon-14 atoms distributed within this sample, which means that the mass overall would be slightly skewed in a mole, averaging out to approximately 12.01. Now, to calculate the relative molecular mass, you simply sum the relative atomic mass of every single atom used in one molecule. For example, in carbon dioxide, there is one carbon and two oxygen in each particle. In order to get the relative molecular mass, we could add the relative atomic masses of one carbon and two oxygen, being 12.01 and 2 lots of 16. The end result, 44.01, is the relative molecular mass for carbon dioxide. This is also the mass in grams if we had a mole of carbon dioxide, and the average atomic mass units in a single compound. A helpful equation to remember is that the number of moles in a substance is equal to the mass of the substance sample over the relative atomic or relative molecular mass of what we're measuring. Let's do some worked examples, shall we? First, we should calculate the relative atomic mass or molar mass of magnesium, and then magnesium oxide. Since there are 3 isotopes, magnesium 24, 25 and 26, we can calculate the average of these. Approximately 79% of the magnesium in the universe is magnesium 24, 10% is magnesium 25, and 11% is 26. We use the averaging equation, 24 times 0.79 or 79%, plus 25 times 0.1 or 10%, plus 26 times 0.11 or 11%. This average is equal to approximately 24.3, which is the number you would see on a periodic table under magnesium for the mass number. That is the mass in grams of a mole of this element. Now, magnesium oxide is only 1 magnesium atom and 1 oxygen. Simple, right? Yeah, of course it is. We add the magnesium's mass to the oxygen's atomic mass, which is 24.3 that we just calculated, plus 16, or 40.3 grams per mole, or 40.3 atomic mass units on average per molecule. Second, I want to use that helpful equation again, and maybe a little bit of logic. Let's use sugar, sucrose to be more specific, as an example. The molecule is 12 carbons, 22 hydrogens, and 11 oxygens. If we wanted to know the mass of this molecule, we do the aforementioned method of adding together 22 hydrogen masses, 12 carbon masses, and 11 oxygen masses. The number in our equation would be the denominator, or big M, and is the mass in grams of 1 mole of this particle. The number of a certain atom in a mole of a substance is simply the number of that element per molecule, multiplied by how many molecules there are. If there is 1 mole of sugar, that means there is 22 moles of hydrogen, 12 moles of carbon, and 11 moles of oxygen. Remember that relative mass changes with how things are bonded. If it is a compound, we want to know how many compound molecules there are, not how many individual atoms there are. If we know 2 parts of the aforementioned equation and want to solve for the third, we can simply rearrange, and most of it comes to understanding which letter we assign each number to. That concludes SACE Stage 1 Chemistry Unit 1.3.